Today is October 8th, the day before my brother Steve's birthday. And this is AP Calculus. Okay, shortcut day. Okay, first shortcut that we're going to learn about is called the derivative of a constant shortcut. Now, there's two parts of this. These are the rules, and you could just believe me, or these are the rules, and I can have to justify them.
We'll believe you.
This one is easy to justify, so I'm going to justify it. If I had a function which is a constant function, meaning every time you give me a new input to this function, I just return the same value again and again and again. That constant function would look like, like this. There's the value a, and no matter what different x value you give me, I just return the value a. We want to ask about what the derivative of the constant function, and remembering that the derivative returns the slope at some given point. So if you ask me over here at -5, and I go, well, what slope does this graph have at -5? Oh, what about here at -3? How about here at 0? How about here at +3? +5. Every time I do it, it's all zeros. Which justifies this rule. The derivative of a constant, and by the way, in this book, we're going to be using the letters A, B, and C typically for constant values. The derivative of a constant is 0. Because the slope is always 0. So there's rule, run, shortcut 1, all done. Any questions? Okay, on to rule number 2. The power rule for positive integers of x. So this is the rule that we're going to use when we have an expression like x to the nth, and n has to be a positive integer. Now again, you can just write down the rule, or I should be forced to prove to you that this rule really makes sense. This is where someone says, it's okay, you don't have to prove it. And I said, no, it's actually relatively easy to prove that this rule is truthful. Now, how many people knew this rule already as we were going through a bunch of the problems earlier? About half of you? This is the rule that basically says, hey, if I have y is equal to x squared, the derivative function for this is, see, this rule says if you have letter n, like n is 2 in this case, bring the 2 down and then decrease the power by 1. So the derivative of x squared is 2x. Now we've actually done that problem using the definition of derivative. Limit as h approaches 0 of f of x plus h minus f of x all over h. We've done that problem. And we came up with 2x when we did that as well. This one also says if f of x is x cubed, f prime of x is 3x squared. Did we do that one in the long form? Hard to say. This one also says the derivative of x to the 4th. Notice I'm using all the different ways that we can say derivative. Isn't that clever of me? Pat myself on the back. All right, the derivative of x to the 4th, 4x cubed. Now again, why is this true? Because I said so. That's great. And a highly ineffective way of making sense of the world. Mr. Fedor, hamburger, cheeseburger. Cheeseburger, why? Because I say so. You don't want to live your life Olivia calling me, do you?
Well,
Texting me, I mean, because you guys don't call anymore. All right, let's talk about the justification then. Let's talk about why this rule is true. Are you ready? If I have a function, and that function is in the form x to the nth, where n is a positive integer, and I ask to find the derivative of that function, the only tool we have are those definitions of the derivative function. And that definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. Is that right? That's got to be our starting point. Well, when this is our starting point and we have this function, we end up getting the limit as h approaches 0 of x plus h to the nth minus x to the nth over h. That's what we get. Now we've done this problem, or at least we've started this process a bunch of times. What in general has been the next step from here? We expand it. All right? And here's what happens when I expand x plus h to the nth power. I get x to the nth. The next term, the x power is going to go down, the h powers are going to go up, and I get x to the n minus 1 times h. And it just so happens the coefficient in front of that term is n. This follows from something called the binomial theorem. And then there's a bunch of other terms, because n could be really big, it could be like 100. And then the very last term, or the second to last term, is like n x to the h, or x h to the n minus 1, and then the very last term is h to the nth, and then we've got this x to the nth on the very end, and all of that mess is over h. Now, what's important about here? Well, when we did problems of this type, what's the next thing that you would do? Cancel that guy out with that guy out, right? Yeah. And now you've got a bunch of terms that remain on top, and then what would you do? You get all of those terms have an h in them, and you would factor an h out. And when you factor the h out of the very first term, you get x to the n minus, sorry, I miswrote that. I get n times x to the n minus 1 plus, and there's a lot of all the terms, and it ends with h to the nth, n minus 1, and that's all over h. Big thing here, by the way, is this next term has an h in it. It's like x to the n minus 2, and there's an h in there. But all the other terms inside the parenthesis all have h's in them, except for the very first term. At this point, after you factor the h out, we cancel out the h's, that's because that's what we always would do. And now we can apply the limit. When h goes to 0, all of these terms here all go away, because they all have an h in them, and as h is 0, they go away. The only term that's left is n x to the n minus 1. And there's our proof of why the power rule works. Now, do you absolutely need to know that to live a full and fruitful life? Probably not. But the lesson here is, it's not because I just say so. Okay?
What would you do if it's like x to negative n?
I'm going to handle that case in a little bit.
Okay.
All right. Rule number 3. The constant multiplier rule. If we are taking the derivative of something in the form cu, now again, a bit of notation. In this book, ABCs are constants. But the letter u, and typically also the letter v, are reserved for functions of x. So whenever you see a u, think of that as a placeholder for some function of x. How about x squared? How about x cubed? How about sine of x? Tangent of x, absolute value of x. Doesn't matter what it is, it's a placeholder for some function of x. No limitations on those functions. So this is really saying I'm taking the derivative of something like this. Some constant, call it maybe 3, times some function of x. How about x squared? 3 is the constant, x squared is the function. 3 is the c, x squared is the u. And what does this rule say? You may take that 3 and find only the derivative of the stuff that's left over. Which is convenient because we have a rule that allows us to find the derivative of x squared. It's the power rule. This is equal to 3 times whatever comes out of the power rule, which is 2 times x. The derivative of 3x squared is 6x. Yes?
Does this come in handy for something else? Because you could just do the power rule. Where you've got 3x squared, you know, 3 times 2.
Do we have a rule that allows us to take the derivative of something in this form? We didn't. No, the power rule was just something in the form x to the nth. This is more than that. But what happens now? We can do the problems of this. If you wanted to create a new rule, you could say the rule for taking the derivative, something in the form cx to the nth, is equal to c times the derivative of x to the nth, which is equal to c times n times x to the n minus 1. Hey, you've got your new rule for you. And now you never have to write it out long ways again. You can go right to that rule. What is the derivative with respect to x of 8x cubed then? 24x squared. Why? Oh, we have this new rule. Take that constant, multiply it by the exponent. There's your 24. Reduce the exponent by 1. There we go. So far, so good? So there's 3 rules. What were the 3 rules again? Constant rule. The derivative of any constant is 0. The power rule. The derivative of x to the nth is n times x to the n minus 1. Last one was the constant multiplier rule. The derivative of cu is c times the derivative of u. All right. Rule number 4. The sum and difference rule. Again, we're going to use u and v as placeholders for any functions of x. If I'm taking the derivative of u plus v, or if I'm taking the derivative of u minus v, I may break it into 2 smaller problems. The derivative of u plus the derivative of v, or the derivative of u minus the derivative of v. We can break up derivatives into little problems based on pluses and minuses. So what kind of problems can we do with this? Well, I know one. We could do the derivative of x cubed, oops, parenthesis too early, x cubed plus x squared. In this case, x cubed is acting like my u. X squared is acting like my v. This rule says, oh, I can break this down as the derivative of x cubed plus the derivative of x squared. What is the derivative of x cubed? 3x squared. How do you know? Power rule. Plus the derivative of x squared. What is the derivative of x squared? 2x. How do you know? Power rule. How did I know that I could break it up into these 2 problems? Sum and difference rule. Now what happens? I'm doing these rules very, very strictly right now. Guess what's going to happen in a week? You just do them. You don't think of them as rules anymore. They're just part of your internal mechanisms of how you do things. Let's do another problem. By the way, anything that's in a yellow box, those are also in yellow boxes in your book. Or beige. Or
Beige.
beige?
Beige cream.
Cream? I don't know. Let's here. Hand me that, Edmund.
It's like the color of that butter you get at Texas Roadhouse.
What? Like beige. Tan.
It's tan.
We get white butter.
I'm asking a female because they know colors.
Beige.
I only know 4 colors.
I
It's
say
like
six.
a
four,
between
yeah.
a tan and
I think the
beige.
light
Between a tan and a beige.
Between, aren't they so light tan?
You're on the
A light
XKCD.
tan.
It's light tan.
Or white, black.
Shut up, you're not tan.
I said, well, I read XKCD, and usually it's,
But he goes to the
It's
concert
like
thing where you have people that come simulate the show, and you know, people all like people the color, and then they say what color.
No, it's not.
And then they did the district.
and actually it'd be very interesting to find out if you did that, whether the distribution of another number of colors that men say is probably much, much smaller than, or has a much smaller average than the distribution of number of colors that females say.
It was actually more equal than thought.
Really? I'm going to have to take a look at that. All right. One more problem. Let's say f of x, this is a different problem, so let me put a line in between here. Let's say f of x is equal to, x to the 6th minus x to the 4th. What's f prime going to be? Well, if I'm doing this really rigorously, saying I can only do the applications of rules, what would you do? This f prime is going to have to be, and I'm going to again use that notation. I'm going to take the derivative of x to the 6th, and I'm going to subtract the derivative of x to the 4th, and when I do that, I get 6x to the 5th minus 4x, that's supposed to be a 4x cubed. Great. Have I mentioned that my wrist really hurts? Yeah.
When did you fall?
At this, I was, you know. And then Mrs. Cameron, she made fun of me when I got over to the sideline.
Mr. Meacham should have fallen so we could sit in your shiny hat.
Mr. Meacham should have fallen because the taller they are, the harder they fall. Mr. Meacham's about this tall.
Oh my.
Maybe he's only this tall. Maybe not this tall. He's tall. He's tall. No one's taller than Mr. Mr. O's like 6'8" or something. 6'10"?
6'10".
All I know is he had to duck to get into my room when I used to work at Lanphier.
I love this room.
So
He's like,
When did you start working at Library?
this is my 5th year at Berkeley. So that would have been what, your 8th grade year? 7th grade
why
year?
did you stop?
That was his.
Because they offered me a position where I could teach calculus and stats and calculus 3 at Berkeley. And when I was at Lanphier, what I taught was computer applications, which is death. It's just a dreadful course.
This is where the power line is.
This is how we do PowerPoint. This is a call out. This is a call out in PowerPoint.
I don't know what that is.
You know what? I'll show you what a call out is.
I had office integration and I still don't know anything about computers.
So I taught that. I taught web page design. I didn't teach any math. I didn't teach any math at Lanphier. So they offered me a
No,
job.
there's no math classes at Lanphier.
There is 2.
There's
There's
no
two.
Geometry, algebra 2, and
Okay.
pre-calc.
Hey, we got to differentiate this.
Oh.
And as we do this differentiation, we're going to actually talk about the rules that we're using. So if I want to differentiate that, meaning I want to find dy dx. Oh, yet another way that we call the derivative of the function y. Okay, how are we going to do this? Well, we're going to use Rule 4, which basically says if I want to take the derivative of something that has a bunch of additions and subtractions in it, I break it into a bunch of little problems. That's the sum and difference rule. And then, what am I going to use to do this part of the problem? Power rule. How about this part of the problem? Power rule and the constant multiplier rule. How about this one? Constant multiplier, and then the derivative of x is actually falls under the power rule. The derivative of x is like the derivative of x to the first power, and so the derivative ends up being the exponent 1 times x, and we have to reduce the power by 1, and we get 0, and x to the 0th is 1. Yes, Nicole?
Wait, so that was just why you would use the constant?
I'm going to pull the constant multiplier out, but when I take the derivative of x, it ends up being 1.
What about in the second one, you said you used the constant multiplier?
Yeah, we pull the 2 out, and then we work on the power rule for the x.
Because it had a constant.
Right.
Okay.
And so there's us doing that. The derivative of x to the 4th is 4x cubed. The derivative of 2x squared is 2 times the derivative of x squared, which is 2x. The derivative of 3/4 x is 3/4 times 1, and then 0. And then when we're all done with that, we clean that up, and we get our final answer. Hooray. Edmund, 6 minutes ago you were supposed to do something.
Oh, yeah. I thought about it,
All right.
actually. Sorry.
Here's another applications of derivatives. Hey, I wonder where this function has, if any, horizontal tangents.
Wouldn't it? Because it,
Let's get to the
wouldn't the derivative be 0 at horizontal tangent?
The derivative would be 0. The slope will be 0 at horizontal tangents. So what are we going to do? We're going to find out when is this derivative function equal to 0. We do that by taking the derivative of our function, finding dy dx, or y prime, whichever notation you choose to use. Should be used to all the different notations. We're going to find dy dx, or y prime. And what is dy dx going to be? Well, it'll be the derivative of
I guess we gotta divide that out.
So yeah, that'll be
of our function, of x to the 4th minus 8x squared plus 2.
4x cubed
Okay, hold on. 4x cubed minus 16. Where's the minus 16 coming from? Turn to your partner right now and explain where the minus 16x came from. Danny, you're partnered with Caprice and Michelle. Did I just call you Caprice? I'm sorry, Caprice is us here and during stats. Candace. They both start with C.
I never knew her name. What'd you say? Does that sound anything?
Candace, Caprice. Yes, they do sound very much alike.
I thought the P and
You still
Oh, okay, I'll tell you. One time during this year, you're probably going to call me by some other teacher's name. You might. People called me last year, the Layfair called me Mr. Brash. They call me Mr. Brash all the time. I don't know why. Mr. Brash, full head of hair, me, bald as a cue ball. Oh, sorry. Right. Mr. Brash and I do have in common, we both have like extremely hairy chests. Except his is more like a gorilla. All right. So, Candace, did you explain to Michelle where that negative 16x came from? Candace, did you explain to Michelle where it came from? Do so right now. Did everyone else get it explained?
Again?
Sarah, you got it? Explain it to me then.
Well, you take the 2 and the x, multiply with the 8, and then you take like
Very good. Danny, did they explain? They did? Everything good? All right. So now that we found out what the derivative function is equal to, now we said, where is this function going to have horizontal tangents, which is another way of saying, where is the derivative going to equal 0?
Factor it out.
Okay, 4x cubed minus 16x equals 0. Turn to your partner, explain how algebraically you're going to find that out. Okay, Nicole, now repeat everything you said. Confirm.
Yes.
Factor out a 4x. When you factor out a 4x, you get 4x times x squared minus 4. X squared minus 4, one of our favorite algebraic things in the world. It's the difference of squares. Okay? And when we do that, we get essentially two different problems. When is 4x equal to 0? When is 4x equal to 0? When x equals to 0. When is x squared minus 4 equal to 0? At 2 and negative 2. So we have horizontal tangents at 0, negative 2, and 2. And we could graph the function, by the way, and confirm that indeed that is the place where horizontal tangents are. Okay, you do not have everything you need to do the homework yet. You get the weekend off. We'll finish this lecture.
You, sir, are a saint. In my eyes.
We'll finish this lecture. But you know what's going to happen on Monday? No. All those people who weren't here. No. You got to teach them. Okay. So what's going to happen on Monday? For the first half of the lecture, I'm going to put these things on the board, but you're going to be paired up with one of the that weren't here. All right. Have a great weekend, everyone.
You too, Mr. Fredo.